Hello everybody, good evening. Let's get started. So it's about time. We're going to solve some examples today. We're going to see an actual physical system, a quantum physical system, which we're going to analyze. So after a short reminder of the Schrödinger equation and what it's all about, we're going to delve into the infinite potential well, which you've already seen in class. We're going to go over it again. Just going to give you some ideas what exactly it's about, and then we're going to solve a lot of examples. So you'll really understand what's going on. You'll see how to solve physical problems using the eigenfunctions and the eigenenergies and so on. And then at home you'll be able to solve even more examples. And by next week you'll be masters of the infinite potential well. That's the plan at least. Okay, so I'll give you a very short reminder what it's all about. What is quantum mechanics all about? It's all about the Schrödinger equation. The Schrödinger equation tells us how the wave function evolves as a function of time. The wave function is what we're interested in. It will tell us the probability of where to find a particle, at which momentum to find a particle, at which energy to find the particle. Anything we want to know, any information we would like to know about a particle in some potential is inside the wave function. And if we want to know how this evolves in time, how this changes as time passes, we have to solve this equation. And we have already introduced the operator notation. We call this thing the Hamiltonian operator, and this thing is the energy operator. So we can write it in operator form. We've already seen how to solve this equation. Since the right-hand side does not depend on time, right? The potential is independent of time. At least for this course it will be. Next semester it won't be. But we'll deal with that then. This side is independent of time. This means that we can separate variables. We can write the function, the wave function, which is a function of both position and time, as a product of two functions, where one depends only on x, one only on t. And as you know, for phi we get the time-independent Schrödinger equation. And for the time, for t, we get the phase. The phase that the particle will accumulate as time passes. So this is the entire time dependence. It's just a phase. Phase means it's e to the imaginary number. That's what we call a phase. And this is the independent Schrödinger equation, time-independent Schrödinger equation. Now, when you solve this equation, you will typically get a set of solutions. You will always get a set of solutions. The set can or cannot be infinite. In most cases it is infinite set of solutions. And that's why we add a subscript n to show that this is just one out of a million equations. There are a million equations like this. The only difference between these million equations is this number. But depending on this number, this solution will be different. So you get a set, not a bit, a set of equations. Set of solutions, phi of x. Right, and then this is why this thing is called an eigenvalue equation, because that's what it is. It's an operator acting on a function, returning a number of a function, so this is called an eigenvalue equation, where En is the eigenvalue and phi n is the eigenfunction. So this is simple. We've seen this before. The general solution of the Schrödinger equation is therefore superposition of all the possible solutions. Right? If one of them works, and two of them work, and three of them work, then all the others also work. And we need to take all of those functions, phi n of x, each of this function, we need to take it with a certain amount. We need to have some indication how much of each function to take. So that's why we add a coefficient Cn. So that's how much of each function to take. You need a sum over all of them. And then each phi n is multiplied by its phase. Each eigenfunction evolves with a different phase, depending on this En, the eigenvalue. So we can add this. We add the phase. And we just take this integration constant and put it inside Cn. We don't care about it. This is psi x of t. So this is the wave function at any point in space, any moment in time, is given by this. Superposition of all the possible states could be in. Now the coefficients, Cn's, they tell us about the probability of finding a particle in the nth state. So Cn squared, absolute value squared. Cn can be a complex number. There's no problem with that. So the absolute value squared is the probability of being in the nth state. To find particle in the nth state. Now if the particle is in the nth state, then that means that its wave function is phi n and its energy is En. That's what we mean by the nth state. It's wave function, right? Its wave function is phi n of x, and its energy is En. That's what we mean by the nth state. It's just a term that we use. We call it a state. We mean that its wave function is given by phi n of x, not a superposition, but exactly phi n of x with probability 1, and the energy is En exactly of that specific n. Let's make an example. So take the wave function. So you have a wave function psi x of t equals 1 over root 3 phi 1 of x e to the minus I e1 over h bar t minus I over root 2 minus 1 plus I divided by 2 times root 6 phi 3 of x e to the minus I e3 divided by h bar t. Okay, so this is a superposition of 3 eigenstates. Phi 1, phi 2, phi 3, let's say that they're known. Each eigenstate evolves with a phase with the energy belonging to it. So E1 comes together with phi 1, E2 comes together with phi 2, E3 comes together with phi 3. And each of them has some coefficient. This is C1, this is C2, and this is C3. As you see, it can be a complex number. So we're fine with that. Now the probability, in this case, the probability of finding the particle in state 1, so I'll call this P1. And what I mean is the probability of the energy being equal to the number E1. That is just C1 squared, which is 1/3. So if the particle is in this state, I'm giving you a particle, I'm telling you this is its wave function, then you know that the probability of its energy being equal to the number E1 is 1/3. Same way, the probability of being in having energy E2 is 1/2, 50% chance, and the probability of being in 3, you need to be careful you take the absolute value correctly,
Has to be 6.
Okay, so you're already thinking about the total, right? But which I want to take the absolute value, it's 1 plus I times I, 1 minus I, that's 2. Here below you get something like 12, so you get 1/6, right? Something's wrong here, I think. It should be 12, right? Oh, it doesn't work. There we go. Squared. So you get 1/6. And as you already pointed out, you obviously see that the sum of all the probabilities, sum over all the n, so you do P1 plus P2 plus P3, you'll get 1. That's just a normalization condition. The wave function is normalized. And obviously the probability of being at some energy is 1. This is how you break it down. So let's have another example. Let's, for this wave function, let's find the average energy. In order to find the average energy, we'll have to apply the energy operator and apply psi from both sides and integrate over dx. Right? So find the average energy. So the average energy E, which we will also write as psi of t, E operator psi of t. The question you want to answer is, you want to find the average energy, and then we want to answer the question, does it depend on time? Someone have a hunch? Will the average energy depend on time, yes or no?
No.
Why not?
Conservation of energy.
That's the quantum mechanical way of conservation of energy. I'll stress the point when we get to it at the end, but very good. So we want to find the average energy. We take the energy operator, which is derivative over time. So we have integral dx. The first one we take out with an absolute value. I'm going to first use the general formula, okay? I'm going to show you how to work with sums. And then we'll implement it for this example. So we have an integral dx, and then we write psi star. Psi star is the complex conjugate of this thing. So there's a sum over Cn star, In star, and there's an e to the plus IE, En over h bar t. Right? Then there's an energy operator. That's IH bar and derivative over time. And then there's a psi. So that's, again, this thing. Sum over n, Cn, phi n, e to the minus I, En over h bar t. Now, in order to work with this, there's a little subtlety here. In order to work with this, I want to shift around different terms. So I want to take this sigma symbol, the sum symbol, and move it to the beginning. I want to move this phi n and put it next to this phi n. I have to be careful because this sum extends only over these three terms, and this sum extends only over these three terms. This sum does not extend over these terms. So in order not to get confused, I'll just switch variables. I'll switch the summing index. This little n, just call it m. It's a dummy variable. So there's no problem doing that. But I have to do this because if I open up the brackets before I do this, I'll be confused. I won't remember which sum belongs to which Cn belongs to which phi n and so on. So it's very important to you to do this step. Now I can rewrite this. I can write sum n, sum m, move them all to the front. I have a Cn star, Cm. There will be an e to the I, En over h bar t. Then there's going to be an operator, and then EO minus IEM over h bar t. And then I can put my integral phi n phi m. Because only the phi n and the phi m depend on space. So everything that doesn't depend, everything I don't have to integrate over, I took it out front. Right? That's the way you solve integrals. Everything that does not depend on the integration variable, you take out front. Look what you're left with. This is simple, this integral. So orthogonal, it's the orthogonality relation. This is just a delta function. It's delta and m. Before I use the delta, I have to solve this derivative. So this derivative is obviously, and there's no other way it could be, it just takes down em. Watch, when you take the derivative over time, we take down a minus I times I, that gives 1. You take down a 1 over h bar, goes away the h bar here, you're only left with the em. So you get em times e to the minus I em t over h bar. This is obvious. It's the energy operator. The energy operator, when it acts on the wave function, it takes out the energy. That's exactly what we were expecting. That's what the energy operator does. So, what do we have? We have a sum over n and m. We have a Cn star, a Cm star, a Cm. Then we have an Em. Then there's an e to the I e n minus Em over h bar t. And there's a delta in m. Right? Now, a delta function, a sum, we love those. Every time we have a sum and delta function, we can get rid of the sum. We just sum over the index m, so use the second one, and replace all the m's by n. Because only if n equals m, this thing is 1. Otherwise it's 0. This is sum over n, Cn squared, because it's the same one, right? Times En, and this thing goes away, because when n equals m, this is 0. So you see that the average energy, right, what is the Cn? That's the probability to be at a certain energy. So you see that the average energy, and this makes absolute sense, I wouldn't have guessed anything else, it's the probability to be at a value times the value. That, we know that since like first grade, right? That's nothing new. And we also see that quantum mechanics reproduces exactly as we would have guessed. And we also see here, obviously, that it's independent of time. And this is exactly what was said in the beginning. The average energy has to be independent of time. Probably you already learned about the Ehrenfest theorem. You did, right? In class. It says that how does quantum mechanics agree with classical physics? If you take the average value, the average of quantum mechanics is classical physics. So energy, on average, has to be conserved. It's independent of time. You see here that and we'll do examples about this shortly, every wave function evolves with a different phase due to different energies. It sounds a little bit like it's a bit weird, and how does that make sense? It is weird, it's quantum mechanics, but on average, we're talking classical physics, and it's conserved, independent of time.
If you wanted, for example, to measure the average kinetic energy or energy over space and not over time, would we have to take the operator of the Hamiltonian?
Okay, what are you saying? You wanna take the average of?
I want to take the energy not as a function of time, but as a function of space.
You want to replace this operator by the Hamiltonian operator?
Yeah.
It's the same thing, because here, applying the Hamiltonian operator on psi or applying the energy operator on psi gives the same thing.
Yeah, so
that's what Schrodinger said.
My question. So
same
we
thing.
Can get the average energy of
by using
space by using the Hamiltonian.
It's not of space, it's the same average energy. What do you mean of space?
No, as a function of space, to know how much energy you have.
It'll be independent of space. No, it'll be independent of space. The energy does not depend on space. Total energy does not depend on space. You're integrating over dx. How can it depend on space? It won't, but you'll get the same. You can try it. Well, here you can't because I haven't told you what phi n is. But if you know what phi n is or a specific problem, you can do it, and obviously it'll be the same. That's what Schrodinger's telling you. And applying the Hamiltonian operator or applying the energy operator is the same thing. That's the meaning of the equation. Okay, just to finish the question. Here we get just, we have all the p's. So the average energy here is just 1/3 E1 plus 1/2 E2 plus 1/6 E3. We said that these numbers E1, E2, E3 are known, so this is the average energy. It's exactly as you would expect from intuition, right? Is the probability to be at a certain value times the value. Sum over all of them, that's the average. That makes total sense. Question about this?
We said that Cn squared absolute value is the probability of finding the particle in the nth states with a specific wave function. Does that mean that if I check if the particle is in a certain state, its wave function is now different?
Yes. Yes. We're not going to talk about it today, but that's called the collapse of the wave function. After you check a particle and you measure a particle in a certain state, then its wave function changes to become that wave function. We're going to come back to that point later in the course, but that's absolutely correct.
So if I want to measure the place and the energy, how would I do it? I will
simultaneously?
Twice? Yeah.
Depends what your system is. It's not necessarily possible. We saw explicitly, for instance, that you cannot measure the position and the momentum simultaneously. Or there's what's it called? The uncertainty.
Yeah.
So if you measure delta, you measure x with a certain certainty, the certainty that you can measure the momentum is limited. Now, if your energy depends on both momentum and position, it makes a problem, right? So if you know your energy, then that means you have to know both momentum and position with a certain uncertainty for it to work. We'll come back to this when we see examples. They're very good questions. We'll come back
if I
to
measure the energy, I know less about the position and the momentum?
or more. I don't know what you knew before. Yes.
We had a debate today about Ehrenfest laws, and one guy said that this is the only connection, this is the only connection that quantum mechanics have to
Classical
with
physics?
classical mechanics.
Okay.
And it's a mathematical connection. Are there any physical connection between the two?
What do you mean? This is physical. What do you mean?
So Ehrenfest law.
On average, quantum mechanics on average is quantum mechanical, is classical. So if you do quantum mechanics, you do an experiment, you'll get a lot of different points and you get a spread. Right? So I don't want to get into any details about a specific experiment. But think about you're measuring the position of a free particle in a Gaussian wave packet, right? So you'll get a lot of different dots. Sometimes it'll be here, sometimes it'll be here, sometimes it'll be in the middle. But if you do it many, many times, and you average over all of them, you'll get some position, right, some central position where the Gaussian has the maximum, that's the average. And that's where the classical particle would be. That's how you would think about the classical particle. I don't know why that isn't physical. Maybe we can talk about this after class if you want to have a few more details. It's an important point, but that's the main connection of quantum mechanics and classical physics, that you are able to reproduce through Schrodinger's equation. You're able to reproduce Newton's laws. That shows that it's consistent. Yeah, that's why it's so important.
After the observation, it collapsed to 1 degree. So the
energy changed.
Difference of the energy. So the difference of the energy is absorbed by the device, by the measurement device.
Correct. It's the person or the device doing the measurement that puts in energy or takes out energy. And that's why it seems so weird that when you measure it, collapses on a certain wave function because you change the energy. It seems energy isn't conserved.
Yeah.
So first of all, it is because you came from the outside, you did something to it, so you put in energy or took out energy. But if you don't touch the system,
Yeah.
right, then the average energy is always conserved. Okay? All right, let's continue. The algorithm for solving any quantum mechanics problem. In a typical quantum mechanical problem, you know your Hamiltonian, and you know your initial wave function. Why do you know that? Because you built a system. You build an experimental setup. So if you built the setup, you know your Hamiltonian. Then you can initialize the system at some initial state. And then you want to find how does the wave function, you want to know how the wave function will evolve in time. So the way you have to go at it, first of all, you're given a Hamiltonian operator and an initial condition psi 0 of x, the initial condition. You then solve the eigenvalue equation. From here you obtain both the eigenfunctions and the eigenvalues. So you have Hamiltonian, you solve this equation. You then plug it in to the general solution. Which is a superposition of all the possible states. And when you do this, right, you found phi n in the previous stage, you found En, but Cn is currently unknown. So in order to find the Cn, you use the initial conditions. You solve for psi of x is 0 at time t equals 0. So this equation, or this sum at t equals 0, is just, the exponent is 1, so it's just Cn phi n. And this has to be equal to the given function psi 0 of x. That's the initial condition. And then from here you use orthogonality to find that Cn is equal to the integral over phi n star psi naught of x dx. And you're done. This is how you solve any quantum system from the beginning to the end. All you know in the beginning is your Hamiltonian operator, because your Hamiltonian defines your system. You know your initial state, obviously. Follow these steps. You'll find the wave function anytime, any place. That's what it's all about. And this is what we're going to do now for the infinite potential well. Solution of eigenvalue equation for infinite potential well. And of course the eigenvalue equation is this thing. It's the short time dependent Schrodinger equation. So what is an infinite potential well? It is the potential given by 0 in some interval between 0 and L, and it is infinite outside. So you can draw it like this. This is x. V, here's L. So it's a well of length L, the potential in the middle is 0, and outside it's infinite. That's what these lines symbolize. it means that it goes up to infinity. I can really draw the line up, so I make those lines here. Now from this potential, we have to find the boundary conditions on the wave function, because we cannot solve a differential equation without having boundary conditions. So we need to find the boundary conditions for this well. And the way we do it is we first look at the areas outside the well. We first look at what happens at x smaller than 0 or x larger than L. What happens in these regions is that the wave function equals 0. Now why is that? There's two ways of thinking about this. One way of thinking about it is that if the potential is infinite, then the probability of the particle being in that region is 0. It's infinite potential, it's being drawn away from it, or pushed away from it, so the probability of being there is 0. Another way of seeing it, it's a little more mathematical way, is by looking at the Schrödinger equation, which of course I have erased. The Schrödinger equation outside the well, right? So there's going to be what's it called, the kinetic energy term, and then there's the potential energy term. Let's make it time independent. One second. Let's make it time independent. Let me just finish the argument. So if V is infinite, right? So this term here is going to be infinity, sort of, times psi, right? And on the other side, we have some finite value, because the energy must be finite. So we have infinity times something must be equal to something finite. That only works if psi equals 0. That's why psi equals 0 if you're in the region outside the potential well. Question?
Sorry for the English question. What is a well?
A
Well.
A well? This is a well.
Wall?
No, well, like when you draw water out of the well.
Oh, okay.
Okay, so we're back again. So infinity times something equals finite. That something must be 0. It won't work otherwise. So we understand that psi outside, to understand that psi of x and t needs to be some psi of x and t inside the well, but 0 outside. This is what we've learned so far. Now, since the wave function is a physical object and it has a physical meaning, but its absolute value squared is a probability. Its absolute value squared is a probability. That means that the wave function must be continuous at every point in space. Its derivative must not be continuous, and we'll see examples for this in about a week or two. But the wave function has to be continuous. This means that psi at x equals 0 for any time t, and psi at x equals L for any time t must be equal to 0. And these are our boundary conditions. We need to find some psi of x and t inside the region between 0 and L, but at the borders it must be equal to 0. This is what you know from wave theory as closed boundary conditions. I'm sure you've seen the phenomena there as well. So you can think of a potential well as a rope with closed boundary conditions. That's what it is. We're solving some wave equation. It's not the same wave equation that you're used to, but we're solving some equation called the Schrödinger equation with closed boundary conditions. Now, obviously, since the wave function is a product of two functions, right? It's phi of x times t of t. So these same boundary conditions also apply for phi. because that's where the space dependence is. Which is an obvious statement. So what we have to solve, right? Have to solve. This is second step here. We have to solve the equation minus h bar squared over 2m d squared dx squared phi of x equals e phi of x. And with the boundary conditions, phi of 0 equals phi of L equals 0. This is simple. You did it in class. I'm going to do it again. It's a very simple ordinary differential equation of second order. Solutions are, well, the children of this equation are both sine and cosine, but only the sine will satisfy this differential equation, these boundary conditions. And there's a second condition, and that is the spatial frequency of the sine must be n pi over L. So from the first boundary condition, you keep only the sine and throw in the cosine. For the second boundary condition, you will get the quantization. The quantization always lies in the boundary conditions. That's why it's quantized, because of the boundary conditions. That's why a free particle, which had no boundary conditions, wasn't quantized. It was a continuous spectrum. You get the discrete spectrum here. Only certain values are possible because of the boundary conditions. And here you are. These are your wave functions, phi n of x. This thing is just a normalization, so that the phi n times phi n integral over dx will give you 1. That's why you need this. Yeah, there we are. So let's make a couple of sketches. So if this is x, and here's L, and here's 0. So I'll plot a couple of wave functions. So we set the wave function with the lowest energy is what we call the ground state. So for n equals 1, that's the lowest energy. We get sine pi x over L. It's half a wave. This is for n equals 1. For n equals 2, we get 2 pi over L, so it's a total wave. It first goes up and then down. So this is the middle, so it'll go up, down, up. This is n equals 2. So you see there's a node. Right, a zero crossing is going to node. For n equals 3, it also starts by going up, but you will now have 2 nodes. So it'll go up, down, and down. And well, it should be equispaced. No. I'm not good at painting. And so on. You see, first of all, that the nth state has n minus 1 nodes. Node is a zero crossing. Right? So the state n equals 1, the ground state, has no zero crossings, besides, of course, the boundary conditions, which are obvious, but it never crosses the 0 in the middle. If you go to n equals 2, you have 1 zero crossing. The more zero crossings you have, the higher the energy. It's a theorem of quantum mechanics. The higher, the more often the wave function crosses 0, the higher the energy. Another thing you can see, if you look at the symmetry axis, this is where my, try drawing this again so you actually see it. So this is the middle, here must be max minimum. still better. So look at the symmetry axis. Symmetry axis of 0 and L is L over 2, it's the middle. So you see that the state n equals 1 is symmetric with respect to L over 2. The state n equals 2 is odd. The state n equals 3 is even again. This will continue this way. You get is that the even numbered states, so n equals 2, 4, 6, and so on, are odd, or have odd parity. It's a little confusing, even and odd here.
If it has an even number of nodes, it's even, right?
If it has an even number of nodes, it's even. That's correct.
Ah, that's this.
Even numbered states have odd parity. That's where it breaks down that we use the same words for numbers and for parity. And the opposite is also true. Odd numbered states that would be n equals 1, 3, and so on, have even parity. Of course, all this is with respect to L over 2, which is the middle. With respect to 0, there's no parity at all because it's 0 on the other side. With respect to the center, which is L over 2, you get this parity, which is nice. Questions so far? Wrong way. Okay, so let's go through one of those typical, I'll leave the algorithm. Let's go through one of those typical exercises. So in exercise, there's a particle of mass m in an infinite potential well of length L, and we want to find the probability of measuring the particle in the interval x and x plus dx. So find the probability to be in the interval x and x plus dx. For the initial condition, A psi 0 of x equals minus root 2 over L sine 7 pi over Lx, and B 1 over root L sine 5 pi over Lx minus 1 over root L. This thing. Okay, so the particle in the potential well. We want to find psi x of t and then take the absolute value squared, obviously, right? So what we want to do is find psi of x and t, and then we'll take the absolute value squared, multiply by dx. This is p of x and t. To be found. This is our objective. Now, how do we do this? So we know our Hamiltonian. We've already done step 2. We've already found the eigenfunctions and eigenvalues. We can now move right away to step 3. So let's start with A. Start with A. So you see, right, this function. We don't have to go through all of the, the integral and so on. It's much easier. You can see right away that this is the eigenfunction. It's exactly this phi n if n equals 7. Right? So you see right away, easy to see. I hate it when people say that, but I hope you can see it. Equals -1 if n equals 7, and 0 for any other n. See that? Yeah? Give me a sign of being alive. You're all asleep. Right? It's obvious that in this sum, only C7 is -1, it says minus sign. But there, since no other signs appear in the sum, they're obviously, the coefficient is obviously 0. And after we see this right away, we can automatically go back here and plug it all in. You see that psi of x and t is just -1, right? Then there's the wave function, which is this thing, -2/7 sine 2/L. Where's 7 come from? 7 pi over Lx times e to the minus e7 I e7 over h bar t, where e7 is just this thing here when you plug in n equals 7, so you get it, 7 squared is 49, so you get 49 h plus squared pi squared divided by 2 ml squared. So I've already found the wave function as a function of time. This is how the wave function evolves over time. The probability to be somewhere in space is just a sine squared times some factor, so it's 2 over L sine squared 7 pi over Lx. And that's it. This goes away. Phase disappears when you take the absolute value squared. Note that this is time independent. And remember this for when we finish solving the second section of the question, and then we'll compare. So that was simple. Told you quantum mechanics was simple. It's about time you believe me. Right? So let's solve the second part of the question. So you see the initial state, right? Initial state is 1 over root L here, and there's something with a sign where n equals 5. And here obviously n equals 7. But the normalization is not exactly what we remember from the wave function, from the eigenfunctions. But if you take a good look, you'll see that you can write this function as 1 over root 2 times phi 5 of x minus phi 7 of x. And that 1 over root 2 will take care of this root 2 that is missing here in each function. Right, remember that the wave functions are root 2 over L. Right, so if you plug this into here, then this root 2 will go with this root 2, and you get this and this. The minus sign is the minus sign. That's it. So you already, it helps if you can look at your function and already recognize which of the terms contribute to the sum without doing any solutions. It's not doing any computations. It's of course much easier. So here you see right away that Cn equals either 1 if n equals 5, minus 1 if n equals 7, and 0 else. Really simple.
We're not supposed to put in the short time in the Cn?
Excuse me?
The root 2, you're not supposed to put in.
Oh, yeah, sorry, you're right. Yeah, of course. Thursday night. Of course. 1 over root 2 and minus 1 over root 2. Thank you very much. Actually, I had it right here, you know. And now the time dependent is 1 over root 2 5x times e to the minus I e5 h bar t minus phi 7 of x e to the minus I e7 over h bar t. What's that? Right, that was, we've done our steps, right? We found the wave function at all times. And now we need to take the absolute value squared of this. Now this is a little bit more complicated here than the previous case, because there are two terms. So remind you, what you have to do is take psi star multiplied by psi times dx. What we get here, we just get a factor of 1/2 out the front. And then from the stars, we'll get phi 5 of x. I won't write a star over phi 5 because we know that our phi's are all real. There's no need to write a star here. It's a real function. Times e to the plus I e5 h bar t minus phi 7 e to the I e7 over h bar t. And then I multiply this by psi. Minus. Now we have to do this carefully so we don't miss anything. Because this is the place which looks, this is the step that looks the simplest, but where most people make mistakes. So be very careful when you do this.
Is it supposed to be an interval or just
No, we're looking for the integral is 1.
So why is there dx?
We talked about this because the probability of being at a specific x is 0 because it's a continuous, space is continuous. So the probability of being at exactly x equals 2 is 0. You always look at the interval of being in some infinitesimal space. And then we call this thing, psi star psi, we call the probability density, right, which has units of 1 over meter. And this is meters, so 1 over meter times meter is dimensionless.
So it is an integral, but not from minus infinity to infinity.
It's an integral from x to x plus dx. Which I'm not going to write because it's just stupid. You understand what I'm saying? It's an infinitesimal space. The thing about continuous variables, the probability of a continuous variable taking an exact value is 0. But if it's a discrete value, right, then you have the problem. That's why you add the dx. You're always in a small interval. Okay, so where was I? I want to multiply these two terms by these two terms. So I multiply phi 5 by phi 5, right? And then I have the phase times the complex conjugate of the same phase. So I just get a phi 5 squared. The same thing happens for the second term and the second term. So you get plus phi 7 squared. But now there are two more terms. There's the first one times the second one, and the second times the first. So now you watch out. Take this one times this one. There's a phi 5 and a phi 7. And now there's an e to the I e5 minus e7 over h bar t. And then this times this is minus phi 5 phi 7 e to the minus I e5 minus e7 over h bar t. Okay, it's the same phase on both of them, but one comes with a plus sign, the other comes with a minus sign. See that? Now this thing, including the minuses, is obviously just a cosine. So it's minus twice phi 5 phi 7 cosine. Call it e5 minus e7 divided by h bar t. Right? And that's it. Because I could write it out all again. But you see now, right on once more, just so we see the answer properly. So it's phi 5, that's just some function of x, right? Squared, plus phi 7, some function of x squared, sine squared. And then there's a function which is both a function of x, a term which is functions of x, and a function of time. So you see that in this case, the wave function is evolving as a function of time. It's changing as a function of time. The probability, sorry, not the wave function. The probability is a function of time. So the probability of being at a certain position is not stationary. Here, it was stationary. No matter what time you measure, the probability to be in a certain place in space is always the same. It's time independent. This one here is time dependent. Now, why did this happen? Why did we once get a time-independent solution and once a time-dependent solution?
Because of the phase.
Because of the phase. The reason is that, well, also here we have a phase, right? There was a phase here as well. But the reason is that here in A, we started off in a specific eigenstate. We started off being in state n equals 7. It was not a superposition. This state is definitely at state n equals 7. So it does not change over time. This is why the eigenstates are also called stationary states. Because their wave function does not change. But if you start off as in a superposition, then each eigenstate evolves at a different rate. So this is saying. The eigenfunction E5, phi 5, evolves at this rate, E5 over h bar, and the function phi 7 evolves at the rate E7 over h bar. So both eigenfunctions are evolving at different rates, at different speeds. And that's why the superposition is changing as a function over time. And there are certain times where a certain location will like give you 0 and different time might give you a different number, right? Because it's a function of time. Okay? Questions about this? Important point, every time you see that you're starting off in an eigenstate, remember, it'll stay that way. Eigenstate is a stationary state. Of course, this is not just true for the infinite potential well, this is true in general for quantum mechanics. In any system you'll be working in, there's always the case. An eigenfunction is stationary, the probability does not evolve over time, but if you're in a superposition, you evolve in time because each eigenstate evolves at a different rate. It's a very general statement of quantum mechanics. You'll see in every system. Okay, let's solve an example about the momentum distribution. Questions about the previous example? No. Okay, so let's continue. Let's talk about momentum distribution. We'll solve an example. We'll consider a particle in the ground state of an infinite potential well. There's a particle in ground state of infinite potential well. Length L, mass m, you know the drill. What we want to find is the probability distribution in momentum space. So in other words, we want to find in general. So this is capital P is the probability, right? And this little p is momentum. Obviously, this is just the wave function Fourier transformed, absolute value squared times dp. dp is like the dx over there. Same idea. So we are told that this is a particle in the ground state. So what do we understand from here?
N equals 1.
n equals 1, right? Particle is in ground state, hence the wave function, at least at time 0, right, is root 2 over L sine pi over Lx, right? And we have just learned that, okay, the wave function evolves in time, but the probability doesn't. And since all we are interested in the end effect will be the probability, we can just not look at the time from the beginning, because we know it'll drop out in the end. So we can save some writing, some pencil, by just not writing it, because we already understand something. We already understood that this is a stationary state. The probabilities will not be a function of time. All we're interested in is the probability. There's no need to include the time dependence here. Is that clear? See, we're learning. Learn something without applying it. It's great. That's how you advance in life. Okay, so all we have to do is Fourier transform the wave function. Sounds simple. We're going to do this in a little special way. You know how to find psi tilde of k, right? What you usually do, we find psi tilde of k. But I'll go ahead and then we say, okay, it's the same thing as p, it's just times h bar. What I want to show you here while we're at it is how to go directly to psi tilde of t, of p. So here, let's go directly to psi tilde of p. So how do we do this? It's the same idea exactly. So, right, we have to Fourier transform, but now we know that since p equals h bar k, it's going to be an integral dp. Sorry, it's going to be integral dx divided by. This is where we get this the addition. There's an h bar here. It's integral dx over 2 pi h bar, and then there's our wave function psi of x, and there's an e to the I plus or minus I. You never know that, minus. And instead of k, there's now a p divided by h bar, because that is k, right, by definition. So I'm doing the same thing. I'm doing integral dx psi times e to the ikx, where k is p over h bar, but there now is another h bar down here. Now why is that? It has to do with normalization, of course. The way I want to...
Because the dp is h bar dk, no?
If there's no dp, there's dx. The reason you see this, think about it like this. Start off with delta k minus k prime. Right? This is the way these functions are normalized. They're normalized a delta function in k. You know that this thing is the integral of dx over 2 pi e to the I k minus k prime x. Right? This is something we've seen this many times. Now let's plug in here this relation. So what we get is the integral dx over 2 pi e to the I p minus p prime divided by h bar x. Right? I haven't done anything, just plugged in. That was a simple step. Now, what is this actually? This is not the delta function of p minus p prime. This is a delta function of p minus p prime divided by h bar. Right? Because the delta function of this thing. By definition, right? So we defined it. Now, it's just a scaling property of the delta function. This is equal to h bar times delta p minus p prime. You proved this identity, I think, in your first homework. So I'm out to use it now. Okay, so you see that a delta of k minus k prime is the same as h bar times a delta in p. Okay, you might be expecting the h bar here because this is the k. No, it's the other way around. Okay, don't get confused. This is the proof. And this implies right, that the delta of p minus p prime must be 1 over the integral dx 1 over 2 pi h bar e to the I p minus p prime over h bar x. Right? So if you just looking at this and this, right? These are equal to each other. So I divide by h bar, right? I get this. So I see that they must normalize. They're normalized, so there's no root here. There's the delta. They're normalized as 1 divided by 2 pi h bar. And that's when I Fourier transform to p directly, and you divide it by an extra root of h bar. Okay, makes sense? Makes absolute sense, right? It's mathematical rigor, you cannot argue with that. Although you might want to. Okay, so let's compute the integral. There are two ways of computing this integral. There's the smart way and the lazy way. I'll do the lazy way. The integral, of course, I'm talking about this integral, right? The Fourier transform into p space. So in order to Fourier transform into p space, I need to solve the integral I tilde of p equals integral from 0 to L dx divided by root 2 pi h bar e to the minus I p over h bar x times the sine I over Lx. First option. You can use sine theta equals e to the I theta minus e to the minus I theta divided by 2i. And then all we have to do is solve an exponent, which is simple. What I'm going to do, simply because I don't want to bore you to death about how to solve these integrals, I'm going to use a very neat formula, which no one knows of by heart, but it's nice to have on your cheat sheet. Okay, so when you integrate a sine times an exponent, you get a sine times exponent and a cosine times an exponent. You take out some factors of a and b's and the various different points. This is what it equals. So let's use this in our case. Sine tilde of p can be 1 over root L pi h bar. I forgot here a root 2 over L. Sorry about that. So the 2 disappears and the L is here. So that happened. And then there's going to be a, where are we? E to the minus I p over h bar x minus I p over h bar sine pi over Lx minus pi over L. That's where it gets messy. And I have to evaluate this integral. I just plugged it in, right? I identified a and b in this integral, plugged it all in, and I have to evaluate this integral between 0 and L. So at x equals 0, the sine disappears. At x equals L, the cosine is 0. So I'm only left with a few terms. I'm left with 1 over root L pi over h bar e to the, sorry, where am I? Here. Pi over L squared minus p over h bar squared. So we get a Laurentian function in p. That was to be expected because we're there's an exponent, so that was to be expected. And then from plugging in into the exponent, we have e to the minus I P over H bar L plus 1. Now what we do with this is we take out half the phase and then have a cosine. So this thing is equal to e to the minus I P over 2H bar L times something, right? So in order to get 1 here, I'll have to do e to the plus I P over H bar L, 2H bar L. And here I already have the half, so I need the second half. So it's e to the minus I P over 2H bar L. See this? This is a very useful trick, which you should always do. Always when you see an exponent plus 1, use this trick. Take out half of the phase, and then you just have to add it here. Because in this case, you now get here twice the cosine of PL over 2H bar. And I don't care about this overall phase, because obviously as soon as I take the absolute value squared, this overall phase will disappear. That's what makes this trick so good. Taking the absolute value squared of this thing is a pain in the neck. You're going to have a lot of terms. You have to start grouping them together. But if you do this first, when you take the absolute value squared, it's simple. So you get a cosine squared. So let's do that. So the wave function looks a little messy, right? It's this times this, right? Times. That's what I'm saying. In any case, we get the probability as a function of momentum, right? This is now a function of momentum. There's momentum here. There's momentum here. So the probability to be at a certain momentum right? It's just this thing squared. As I already said, the phase will drop out. Everything else is real. There's nothing really that we have to do. So we just get 4 divided by pi h bar to the third L divided by pi h bar squared minus LP squared. This whole thing squared. I also multiplied the entire equation by h bar L squared to get upstairs. So I won't have double fractions. That's just a matter of taste. Times the cosine squared L over 2h bar times p, and then there's a dp. Okay? So this is the probability. It's a Lorentzian squared, right? Multiplied by a cosine squared. Now, does this look like a legal probability distribution? Or could this be problematic? Actually, not Lorentzian, I'm sorry. There's a minus here. Lorentzian is a plus. There's a minus here. Does that make you worry a little bit? What happens if P is the variable, right? So what happens if P equals pi h bar over L? So what happens if LP equals pi h bar? And this thing is 0, and then the probability diverges? What? Nobody's worried about that? I don't know if you know, we can continue. Okay, of course you're worried about this. This cannot be, and the truth is it isn't. Okay, what happens? Always do sanity checks. When you finish calculation, don't just go on to the next question. Although there are a lot of them, do a sanity check. What happens for P equals pi h bar over L? Right? It looks like this thing should be 0 and it'll diverge. But what you actually get, if you have to look at the entire function. So what happens to the cosine? So this thing diverges. But you'll see that this thing is 0. Look at the cosine. So you get a cosine squared of L over 2h bar times P, which is this thing now, pi h bar over L, which is the cosine of pi. Or pi over 2, sorry, it's cosine of pi over 2. So it's 90 degrees, that's 0. So 0 divided by 0 Now I can take the limit properly, right? Do some L'Hopital or some fancy theorem that you know from mathematics, you will find out that if you do this limit properly, and I'll leave that to you, you'll get a finite number. It actually makes total sense. It's important to check these things. This also means, right, there's one more thing I want to tell you about this function. See from it, right, it's a cosine, and a cosine is periodic, and it can become 0. Right, it's a cosine square, right? It's always positive. Obviously, it's a probability. It must be strictly positive. If you look at the function, probability is a function of p. It looks somewhat like this. So there's a maximum at p equals 0, then drops off, and it then makes these oscillations. It becomes smaller. And this point here, halfway to the first 0, this is the point that we were afraid of. This is where p equals pi h pi over L. But since the cosine would also be 0 there, we have 0 divided by 0, we get some finite number, which is just the number of the curve there. And then at 2 times this value, it's 0. 3 times this value, it's 0, right? That's where the cosine has its zeros. So this also means that these values are momentum values that the particle cannot have.
Kind of reminding the double slit experiment, the shape of the graph.
Yeah, but it's not. A double slit? A double slit will give you a sine squared.
Double slit. Yes.
And if you're going through a square, there's a diffraction through a square well, you'll get a sink, which looks a little bit similar, but it's not a sink, it's this function. I've never seen this in a double slit experiment. It also will give you a sine. Goes to delta, and the delta gives you a sine. Okay, so it's periodic in 0. You have all the zeros. The first place we expect is 0 is not 0 because the denominator also is 0. You get a finite number, and there are certain values of the momentum which the particle in the ground state. Right, we're talking about a particle in the ground state. You raise the question. We're talking about a particle in the ground state of the infinite potential well. There are certain values of the momentum which it has at a high probability, certain that it has at a low probability, and certain values that it cannot take. Just an observation. Questions about this? Okay. Who's tired? Who's not? Okay, last example for today. For the remaining 15 minutes. Let's solve an example that has to do with the Ehrenfest theorem. We'll consider a particle of mass m in an infinite potential well of length L, and it has the following wave function. It's a superposition between the first between the ground state and the first excited state. So the wave function is given psi x of t is 1 over root 2 phi 1 of x e to the minus I e1 h bar t minus phi 2 of x e to the minus I. Okay, that's given. And the question is verify the Ehrenfest theorem, which is verify one of them. That's the one saying that momentum is the derivative of time derivative of location, position. P equals m dx dt. Of course, is only true on average. We're going to verify the Ehrenfest theorem for this wave function. It's true, of course, in general. We know it's true. Of course, you could just prove the theorem in general and say, so obviously it's true in particular, but we'll solve it here in order to see how it's done. We might even learn something on the way. So what we have to do, here's our to-do list. We need to find the x, the mean position, and then take derivative. And then we'll have to find the mean momentum. Okay, let's get right into it. The mean position. We already are in position space, so this is easiest done. It's very easy to do this in position space, obviously, of course. So we'll multiply. So we'll take this wave function, take the absolute value, right? It's psi of t, x operator, psi of t, right? So we get 1/2. I'm missing an integral, right? Integral dx, phi 1 of x e to the minus I e1 over h bar t. Did I have a plus sign or a minus sign? Yeah, the minus sign. No, they were lost. Doesn't really matter, but just be consistent. E to the I e2 over h bar t. Then I multiply by x and multiply. How am I doing this? No minus sign here. It's the complex conjugate. And then there's a phi 1 of x e to the minus I e1 over h bar t minus phi 2 e to the minus I e2 over h bar t. This board is too short, or the exercise too long, you decide. Okay, so we do this. There are actually 3 integrals to solve. Right, the first integral is x times phi 1 squared. The second integral is x times phi 2 squared. And then the third integral, I'm not going to do it all explicitly again. You already saw that when the third and the fourth term from here give you a cosine. We've seen that already, so I'll just get right to the point. It's the integral dx of x times phi 1 times phi 2 times the cosine of omega 2 1t, where I have denoted omega 2 1 is e2 minus e1 divided by h bar. You can verify that the energy divided by h bar has the units of a frequency. It's obvious from here as well, because it's times t, so it must be, the exponent must be dimensionless. But you can verify this also explicitly. So there are 3 integrals. Now, if we're smart, and we are smart, we're not going to go and solve all of these integrals. We're going to think ahead, because in the next step, we're going to take the time derivative of this. Now, if you look at the 3 integrals, which are actually here again, look at the 3 integrals, only one of them depends on time. Obviously, these 2, after I take the time derivative, which is the next step, right, this will be 0, this will be 0. So I'm not going to calculate it and then just put in 0. I'm going to drop it from now already, and right away calculate on this integral. Okay? That's why it's good to be smart. You work less. So let's do it. So ddt of the average x, right? I already take this integral. So we get minus, I'll plug in the functions now, minus 2 over L ddt integral dx times x times sine pi over Lx times sine 2 pi over Lx times the cosine I could have taken the cosine outside as well. Right? It doesn't. The integral only extends up to here over x. In any case, you can solve this. I'll just come right to the end. I think we're approaching the end of the lecture, so I'll just come right to it. And whoever doesn't believe me can go over it at home. I trust you that you will. So I'll take the derivative and the integral all in one step. If no one goes over it at home, I'll give it in your next exercise, then you can all do it at home. Okay? I know you love homework. Why am I doing this? I'm doing this back to front, okay, but never mind. 8L squared over 9 pi squared. So compute the integral, and now I'll plug in this omega 2,1, because we know what it is. It's just E2 minus E1, and we know the E's as well. They include all sorts of pi squares and L squares. So if you plug in this omega 2,1 here, then we'll get rid of some of these constants here. So it's a good idea to plug it in, and we'll get minus 8h bar divided by 3ml. That's this L, that's why there's one left. Times sine omega 2,1t. Okay, great. That's ddt of, this is the average velocity if you want. It's not really the average velocity, it's quantum mechanics, but it's the derivative of the average position. Next step, we want to find the mean momentum. Okay, so for the mean momentum, there are two options, as you know. Either you Fourier transform and use P operator equals P, which is multiplication by P, or you can stick with psi of x and use the derivative. I don't know what is easier in this case. They're both a lot of work. The way I go in my notes is I stick to the second way, because taking the derivative of a sine is of a cosine, sorry, of a sine. Taking the derivative of a sine is quite easy, and then I have integrals of sine times cosine, which are usually not that difficult because I can use symmetry arguments. I know that they're both periodic. I know the period is either half of the wavelength of the length of the well, or twice the length of the well. So I can use also symmetry arguments to solve that. So I don't know if it's less work than doing the Fourier transform, because you saw the Fourier transform of the sine is also not that simple. So I just stick with the second way, but I'm not sure it's less work. In any case, so what I'll do is the integral psi star minus IH bar ddx psi squared over dx, and then just jump right to the end if you want to. There are a total of 4 integrals to solve, 2 of which evaluate to 0. Right, the 4 integrals, that's obvious, because there are 4 terms. When you multiply them, 2 of them evaluate to 0. That's what I meant by the symmetry arguments. So use symmetry arguments, 4 integrals. 2 are equal to 0. 2 you compute. Big smiley face. And what you get is obviously, right, not big surprise, minus 8h bar over 3L sine omega 2,1t, which pretty much is what we got over there. We're just missing multiplication by m, right? So if you now multiply this by m, right, that's what we have to prove. So prove Ehrenfest. We multiply this thing by m, so the m here disappears, and you get exactly what you have here. And we're done. So there are a lot of integrals. Be smart, you'll only solve half of them. this homework looks a little bit shorter than last time. And